Okay, so thanks for coming. I want to thank the organizers too, so I get to conclude this workshop. And I'll be talking about disentangling mixtures of Gaussians, and this is based on joint work with Adam Klein and Greg Valiant. So let me start this talk off by first telling you that I'm not a statistician, I'm an algorithms person. And what I'll be talking about is revisiting some classic learning and statistics problems, but from the perspective of algorithms. Trying to understand, do we actually have matching algorithms which have reasonable running time that match some of the well-known estimators in, say, statistics. So let me start off with just something basic, just to make sure we're on the same page. This talk is about mixtures of Gaussians. So these are a very simple distribution on Rn, which let me for now confine myself to mixtures of two Gaussians. So the way that we generate a random sample is we take a biased point, which is heads with probability W1 and its tails with the remaining probability W2, and we flip it. And if it comes up heads, we take a random sample from the first Gaussian component, we output it. If instead it's tails, we take a random sample from the second one. So the density function we get now is just very simple. It's a convex combination of the density functions of the two constituent Gaussians. So this is of course very basic, but maybe now I should come to the question of why are mixtures of Gaussians important? So actually, to do this, let me tell you a story that dates back actually to the 1890s, back to Carl Pearson, who was a very famous statistician who was interested in evolution. So there's a particular species of crab called the Naples crab that inhabited the region around him. So what he did was he took many samples from this crab population. He measured some physical characteristic of each one. In his case, what he measured was the ratio of the height of the crab to its circumference of its head, for some reason. And he plotted the frequency of occurrence of different values. But what he got surprised in, because this aggregate density function wasn't Gaussian, it wasn't even symmetric around its maximum value. So what he postulated was that maybe the species of crab was not one species, but rather two, and that the density function he observed could be explained as a mixture of two Gaussians, corresponding to the two species. So actually this sets up this algorithmic question of, given what we believe are random samples from a mixture of two Gaussians, are there good algorithms for estimating their parameters? So that's the focus of this talk. And of course, Gaussian mixture models have tons and tons of applications. And I want to mention that actually there are many classic statistics solutions. You can think about something like the maximum likelihood estimator, which they're a good balance for how quickly this converges to the true parameters. How many samples do you need to get good estimates to the underlying mixture of two Gaussians? But the issue is that these estimators are computationally hard. So when you actually talk about an algorithm trying to compute these estimators, they actually run in exponential time, are the best known algorithms. Or you can talk about things like the EM algorithm, which are things which can be implemented efficiently, but they have the trouble that they don't actually have any guarantees. They can and do get stuck in local optima, so they don't necessarily recover the true parameters. But instead, what we'll ask is, can we provably recover the underlying parameters, and can we do so with an efficient algorithm, one that runs in polynomial time? And so just to set up some of the past history of this work, this is a question that's been adopted within theoretical computer science. So just a notational convenience, I'll use D to denote the statistical distance between two distributions. And a lot of the classic work on this problem is actually based on clustering. It's based on the idea, for example, if we have mixtures of Gaussians which their components are extremely far apart. So for example, their centers are root n times the largest variance apart, then in fact what you can do is you can project onto a lower dimensional subspace and these clusters will still be relatively disjoint. And that way you can cluster which data came from which component and just spit out the empirical mean and empirical covariance. So these actually yield algorithms, and these separation conditions were progressively improved until the work of Aurora Kannan, who improved the separation to n to the 1/4. And in fact, this was later improved to a separation condition which only depends on the number of components. So it doesn't actually depend on the intrinsic dimensionality of the problem. Amplioptis, McSherry, Vimpala, and Wong were able to get separation that only depends on the number of components.
What is K?
So K will denote the number of components of a mixture of Gaussians. In this talk, for simplicity, I'm going to focus on 2. But everything I'm saying will extend, actually, with a lot of extra technical work, to the larger case. I want to mention one other result, which is you can think about, actually one case of mixtures of Gaussians, which is not handled by any of this previous work, is something that Brubaker and Van Pollak called the parallel pancakes example for obvious reasons. Is you could imagine you have two mixtures of two Gaussians, which have very small variance and very small separation in that direction of small variance. So actually all of the previous algorithms still failed for this particular mixture because the largest variance is quite large compared to their separation. Now I want to mention that actually all these previous results were fundamentally in a regime where the two components are very far from overlapping. Their statistical distance was close to 1. And there's a very simple reason why those algorithms needed that condition was because they were based on clustering. They were based on the idea we want to take many samples from the mixture of Gaussians and be able to tell which component generated which of the samples. But now what happens when these two Gaussians, instead of being very far apart in statistical distance, are actually very close together? Then we very quickly encounter a sample which we don't know which component generated. So actually this talk will be about, can we learn the parameters of mixture of Gaussians without clustering? And can we go beyond this barrier of having algorithms that only work in the case where the statistical distance is close to 1? Can we get away with statistical distance close to 0? So the Gaussians are now not almost entirely disjoint, but are almost entirely overlapping. So let me just set up some definitions that tell you the main theorem, and then I can sketch for you the ideas. Well, I'm going to say that a mixture of two Gaussians is epsilon statistically learnable if each of the mixing weights is at least epsilon, and the statistical distance between the two components is also at least epsilon. So we're in a totally different regime. These two Gaussians just need to be non-negligibly different from each other in order for these algorithms to work. In fact, what we showed, so our goal will be to learn this mixture on a component-by-component basis. So we want to learn another mixture of two Gaussians. Now we don't know which one corresponds to component 1, which one corresponds to component 2, but we want what we've learned to have a matching to the true mixture, so that across this matching you get the mixing weights right, you get the means right, and you get the variances right, within some additive epsilon error. So that'll be the goal. And in fact, the main result in this paper is that we show that, in fact, there is a polynomial time algorithm to learn a mixture of two Gaussians with no separation condition. So just to put this in context is that the only previous approaches for doing this were things like the maximum likelihood estimator, which then are hard to compute. So in fact, there was no algorithm for the statistical problem whose running time was better than exponential, even for mixtures of two Gaussians in one dimension. And something that I won't talk about is that actually these ideas can be extended to work with mixtures of k Gaussians, but just for simplicity, let me focus on k equals 2. So those are the main results, and now let me tell you, yep.
So do you need epsilon to be the same in the two, so you had two epsilon. One was for the accuracy and one was on the assumption on the statistical distance.
Right. So you can, you can have different epsilons. That's not a big deal. Okay. That's just, so that first epsilon is just a lower bound for how many samples you would need to have in order to learn on a component by component basis. Because for sure you need at least one sample from each Gaussian and one sample from the non-overlap region. But once you have such a guarantee, then you can actually drive the error down to any epsilon you want. So good question, though. Okay, so let me tell you the rough idea. And actually, the rough idea will be pretty simple, but there'll be a lot of issues with it that we'll have to try and overcome. So the idea is to take this high-dimensional learning problem, suppose we're in n dimensions, and to actually try and reduce it to a series of one-dimensional learning problems. And we're going to run a univariate learning algorithm, which I haven't specified. We'll have to give a new univariate learning algorithm. But the idea is that we'll be able to piece together these different instantiations of this univariate learning algorithm to actually get estimates on the higher dimensional parameters. Each direction which we project on and have a univariate mixture of two Gaussians, when we learn its parameters, those parameters are going to give us constraints on the higher dimensional mixture of two Gaussians, which then we can solve this linear system to actually obtain provably good estimates in higher dimensions. So that's the basic idea. So let me walk you through how exactly you can get this idea rolling. So just to try and substantiate this plan, well, the first trivial claim that I'm sure everyone knows, we take a high-dimensional Gaussian, so it's got some high-dimensional mean and covariance matrix, and we project it on some direction R. Then what we get out is we get out a Gaussian. But moreover, the mean of that Gaussian is just the projection of mu1 onto R, and the variance is just the quadratic form of R on sigma 1. So the point of this is that if we had a way to learn the parameters of a...
What is x? What is x?
So this is just, I mean, it's a density function, so this is over x, which you put in, and it'll plug in and give you the density. So nothing fancy there. But my claim is that what this implies is that if we can learn the parameters on different projections, then knowing those parameters, knowing the mean and variance, give us linear constraints on the high-dimensional parameters. If I had a single Gaussian and I learned its projected mean and projected variance, I could use that to get one linear constraint on the high-dimensional parameters. So now we're actually going to encounter our first problem. So I'll use dp to denote the parameter distance between two different Gaussians. And the first issue is that if our goal is to try and project this mixture of two Gaussians onto different directions and run a univariate learning algorithm, what happens if accidentally when we project it, the two components look very, very similar? So their parameter distance is very small. This would be a very serious issue because then we'd have to run our algorithm with extremely fine precision to see the difference between these two components. So this isotropic projection lemma, which is one of the main technical pieces, is that we showed that if the mixture of two Gaussians is in isotropic position, which you can without loss of generality assume, then in fact this never happens. So the intuition is, suppose we had our high-dimensional mixture of two Gaussians. Now we want to show that when we project it onto a random direction, its parameters are noticeably different. So what if I take a vector u which connects their means, and now when I project this mixture on a direction, well, the difference between their means looks like the projection of u. So in the case where these two Gaussians have any sort of difference in their means, we already know that on a typical direction, their projected means will be reasonably far apart. But what happens if their means are the same? So this is where the meat of the idea is that if you have two different Gaussians whose mean is the same, but they're not the same component, so they have some non-negligible statistical distance, then the only way that can be possible is if their covariances look different. So when you project it onto a random direction, their variances look different. So this is the first idea, is that now we can actually project this mixture of two Gaussians onto random directions and try and run a univariate learning algorithm. And the idea is that now when we project it on some direction R, we're going to learn two components. And when we project it on some direction S, we're going to learn two components. But one of the issues is that in this univariate mixture of two Gaussians we learn, the parameters of the first component yield a higher dimensional constraint on the higher dimensional Gaussian. But how do we actually match up these constraints across each of these different projections in a way that they're actually consistent? So the idea is that actually when you project to a direction R and you vary it continuously, the means, the projected means also vary continuously. And the same is true with the variances. So the idea is that if you project onto a direction R and these two components are different in either their means or covariances, when you search nearby directions, it'll be easy to match up the components. Because whichever one had higher variance on the direction R will still be the one that has the higher variance on direction S. So now the idea is that to put the entire thing together, the idea is that when we project on a direction R randomly, we know from the isotropic projection lemma that the two components will be noticeably different. And then when we project on nearby directions, we know that that same comparison is maintained. Whichever one had the larger mean will also have the larger mean in this projected direction. So when we run our univariate learning algorithm, we're going to learn a different mixture of two Gaussians that's close to the truth. And we're going to get some different mixture of two Gaussians in this other direction. But now we can actually pair them up so that they correspond to the same component. So in this way we can get many linear constraints on the high dimensional parameters of the mixture and actually recover provably good estimates to the underlying parameters. Yep?
How do we choose the nearby direction? You choose some, you have some bandwidth there, and then you choose randomly the nearby direction, or?
Well, okay, so let me be more precise. The idea is when you project on a random direction R, either the means or variances will be noticeably separated.
Uniformly random, yes, uniformly.
Uniformly random, once you put it in an isotropic position.
Yes,
Exactly.
important.
So let's, for simplicity, say the means were different. I'm claiming that any direction S that's sufficiently close to R will actually move the means not too much. So provided that amount that it moves it is not too much compared to the initial separation, that means that they're in the same order here. The same is true for the means or for the variances. So it's sort of, all these epsilons come from sort of different problems layered in. The first layer is you have some error in your univariate learning algorithm, that's epsilon 1. You have some notion of the separation condition you allow between the different directions, that's epsilon 2. And epsilon 3 is how large this typical separation is. So actually epsilon 3 governs epsilon 2. However large that separation is controls how far you can move before you lose the ability to pair. And that epsilon 2 is what controls the condition number of solving the higher dimensional system of linear constraints. And all that means is that you then have to learn the parameters in one dimension much better. But it's still a polynomial relationship. So that's, yep. Is there another question?
So about the dimensionality of the problems, do you assume a big dimension? Because if you have 2 points separated in high-dimensional space, and then project down to 1 dimension.
Divide the distance by root n, right? So the focus of this talk, though, is on any polynomial time algorithm. So as long as the 2 points were already reasonably separated in the higher dimensional space, they'll still be non-negligibly separated there. The question here is the distinction between polynomial and exponential. So at least the random projection, even though it scales it by root n, it still preserves the fact that when I learn it, to that accuracy, it's only a polynomial factor small. Any other questions? Very good questions so far. So, yep.
I think you didn't answer David's question. So
Okay.
he was asking about how do you choose the next direction. So do you choose a bunch of direction uniformly at random and then you patch everybody together?
Yeah. So yeah, exactly. So this is, this is fairly involved, but essentially the intuition should be that the closer the directions are, the closer the constraints I get in high dimensions are to being redundant, right? That controls the condition number of the system. But if you choose it uniformly at random from points that are some distance epsilon 2 away, the condition number, if you do it right, will actually be bounded by some polynomial in n and 1 over epsilon 2. So, you can do it any way you want, provided that you can analyze the condition number of that system of linear constraints you get. Is that fair? Okay, so all of this work was just to show you how to reduce an n-dimensional problem down to a one-dimensional problem. But what I still haven't answered is how do you actually learn in one dimension? So now actually we revisit Pearson's original problem, which, so can we learn some additive approximation of the true parameters in one dimension? So first let me do something which I'm going to make this problem sound completely trivial from an algorithmic standpoint. Then I'm going to tell you why it's not quite so trivial. So, the first question is how many free parameters do we have? So actually we only have 5 free parameters for a mixture of 2 Gaussians. All we have is the mixing weight, mean invariance, and mean invariance. So why not just do some sort of brute force search over all of these parameters? As long as all I care about is polynomial time, this is still okay. But actually the tricky part for the one-dimensional problem is not showing that the true parameters will pass your test. It's showing that there's no other setting of the parameters that somehow passes your test. Another way of putting it is we might a priori be worried, why aren't there 2 different settings of these parameters which create very close distributions? So that's the thing that we have to analyze, is that that we never get fooled with a wrong guess. That there actually is only one true set of parameters that we could learn that explains the distribution. And in fact, the way that we did this was actually by revisiting Pearson's original approach, the method of moments. Yeah.
But maybe this wrong set of parameters will be ruled out in the second projection when you do it.
You could. that ends up getting, I mean, maybe that could save you. I agree that this isn't an ending mistake. But if you think about it, you wouldn't even be able to do mixtures of two Gaussians in one dimension without being able to answer this. Because you could a priori have two different sets of parameters that are not close to each other, but their distributions are exponentially close. This is why things like identifiability through like Tyker's results that go through the tails, they don't yield anything better than exponential because it takes too many samples to actually realize that difference. But in any case, I'm actually going to give a reinterpretation of Pearson's original 6-moment test that actually goes through the heat equation, and that'll be the last punchline of this talk. Which, let me ask a weaker question. Right now, just to make sure we're on the same page, we're asking, why can't there be two different mixtures of two Gaussians that look very similar, even though their parameters are different? And the way that we'll do it is, we'll first attack the question, why does one of their first 6 moments differ? So if we have two different mixtures of two Gaussians, one is the set of red components, and the other is the set of blue components, the first thing I'm going to do is I'm going to show you that actually they have to differ on one of their first 6 moments. So let's do the following thought experiment. Let's take this red mixture of two Gaussians, and let's pointwise subtract this blue mixture of two Gaussians. And what we get is we get some function along the real line. It's this green function. And it crosses the 0 axis some number of times. What I claim is that actually what we're really looking for is to understand how many times this green function can cross the 0 axis. Because what if, hypothetically, it only ever crossed the 0 axis at most 6 times? What I claim is we could then fit a degree 6 polynomial to the sign difference. And that will imply that they differ on one of their first 6 moments, because they have different correlations with some degree 6 polynomial. Or to put it another way, what if f minus f hat cross 0 at most 6 times? Then when we integrate this degree 6 polynomial against the difference in their density functions, we get something strictly greater than 0. And we can just expand out whatever this polynomial is. It only has 6 terms. We can use the triangle integral. But now when we get the integral of x to the r against the difference in the two density functions, what we get is the difference in their first 6 moments. So what this means is that actually if their first 6 moments exactly matched, we would have a contradiction. That we have 0 is greater than 0. So in fact, the statement that f minus f hat crosses the 0 axis at most 6 times is what implies we have a good contrast function for the two different distributions. Is that we actually can show that one of their first 6 moments is different. And the main technical work is to show that it's even noticeably different. But the last part that I'm going to tell you about is the statement of the proof of this, that actually one of the first 6 moments is different for two different mixtures of two Gaussians. And so recall, what we're really trying to prove is the number of times this function crosses the 0 axis. So let me, for simplicity, let me abstract it this way. Let's suppose we have a linear combination of k Gaussians. So we're allowing addition and subtraction of them. And in our setting, we would have a linear combination of 4 Gaussians. And what I want to show by induction is that the number of 0 crossings is at most 2k minus 2, which would give us 6 for the setting we're interested in. And in fact, what I'm going to do is I'm going to pull out an obscure theorem from analysis, which is going to sound non-intuitive, but let me make it more intuitive. It turns out that here's a really amazing property of Gaussian functions. If you take any function along the real line and convolve it with a Gaussian, you don't increase the number of 0 crossings. So in fact, there's a heat equation interpretation of what this is. Because you can think about f of x as being some sort of heat profile along the real line. And asking what that profile looks like at some later time is like convolving it with a Gaussian. So the same way that allowing diffusion doesn't create, can only smooth the function, doesn't create new local maxima because you pull them back down, doesn't create new local minima because you pull them back up, the same way diffusion doesn't create extra 0 crossings. So now the idea is that we can prove this by induction. So let's assume we have this linear combination of 4 Gaussians. We're adding the 2 red ones and subtracting the 2 blue ones. Now what if I take the thinnest Gaussian, the one with the smallest variance, and I subtract that variance from all of the different components? Everything gets narrower except one of the components becomes a delta function. So if I ignore that delta function, I now have a linear combination of 3 Gaussians, which by induction has at most 4 0 crossings. But here's the trick, is what happens when I add back in that delta function? I can add at most 2 zero crossings, one on the way up and one on the way down. And now how can I recover the original linear combination of 4 Gaussians is by convolving by a Gaussian of that variance that I subtracted off. But that doesn't increase the number of zero crossings. So this implies by induction that the first 6 moments are different for 2 different mixtures of 2 Gaussians, and actually proving a quantitative version of this, of how different they have to be, is then what gives us a univariate learning algorithm, and then we can plug that into the higher dimensional problem and get the main results in this talk. So that's it. So thanks.
Very good. Interesting talk, and discussion is open.
So I think I'm just a bit confused. So at the end, why do you need at most a certain number of crossing and not at least a certain number of crossing?
So at most gives me a bound on the degree of the polynomial that I get to match the sign of it. So as long as it's at most 6 zero crossings, I get a degree at most 6 polynomial, which implies that the 2 density functions have different correlations with some degree 6 polynomial. So hence they can't have the first 6 same first 6 moments.
And what if you proved, if it was not a constant, if it was something that would depend, well, you have only 2, okay.
So it turns out, so that analysis is actually tight for k. So, that actually, you actually do need a linear number of moments for mixtures of k Gaussians to distinguish them. But in fact, we even showed in a follow-up paper a statistical lower bound, that there are 2 different mixtures of k Gaussians that have very different parameters, but are exponential in k close. So on the one hand, this notion that you need linear in k number of moments tells you that the algorithms you derive only have exponential and k dependence, but that's actually inherent.
Is it robust to contaminations of the Gaussians?
So no. So the clustering results end up being more robust to this. But something that I'm sort of very curious about is, if you think about information theoretically, the limits, of adding some amount of error to the density function doesn't change the fact that information theoretically you'll still be able to recover good estimates of the truth. But any sort of contamination error, it actually produces very different computational complexity. So, even in things like packed learning, even though we have a few packed learning results, as soon as you move to the setting where you have some fraction of corruptions, and you move to an agnostic learning standpoint, we have no general algorithms there. So I think that's more a property of we don't necessarily have good models for what the noise should be in order to actually give positive results there, in my opinion. But I think it's a very interesting question. We can maybe discuss it more. Yep.
I have a remark about formulation of the problem. 6 years ago, Clark published a well-known paper about projection of convex bodies in high dimension.
You have a central limit theorem for the projection.
Yeah. Normal distribution and projection. You know about it.
Yeah.
And how your result can be applied to investigation of convex bodies in high dimension.
I think that's a very interesting question, is that, so the issue is the uniform convergence you get for those types of things.
Yes,
is it
it's
strong enough to be able to
uniform.
handle? Now, the reason I'm not so optimistic about those things is that there's sort of some classic hard learning problems, like noisy parity, which actually have a very similar flavor, that they end up being discrete distributions in high dimensions, which their projection looks like a discrete mixture of Gaussians in some sense. So there are issues that, even though you can get these like central limit theorems for the projections, the error bounds that you get in how close you are to actually being a mixture of 2 Gaussians is really crucial, in that people actually believe some of those problems are computationally hard.
Another question?
What if your parameters were epsilon separated but multiplicative as opposed to additive? would that the running time, because now your running time does not depend on the size of parameters, right? Mu and sigma
Yep.
are relative.
So, okay, so there is some stuff that I swept under the carpet just for simplicity. So the general statement that we get in high dimensions is that as long as the mixture of two Gaussians, their statistical distance between the two components is at least epsilon, then you're in good shape. So in fact, like a good example to keep in mind is that if you have two parallel pancakes like this, right? You can have arbitrarily small separation measured geometrically, even though their statistical distance is very large. So the issue is that that's a mixture which is not in isotropic position. So, when you're in isotropic position, you can, create, there is a bidirectional relationship between the statistical distance and the geometric distance. But it's really when you're not in isotropic position that you have to worry about it. Now, the result that I stated in the beginning of the talk, that works for any mixture of two Gaussians, and it assumes a statistical separation. But that actually is a big issue. So actually for mixtures of k Gaussians, for k larger than 2, this is the really serious issue that comes up, is that this is a mixture of 3 Gaussians, which is in isotropic position. But if you think about it, when you project it onto a random direction, it's exponentially close, arbitrarily close actually, to a mixture of 2 Gaussians. So in fact, what you have to do in this setting is you somehow have to learn a mixture of 2 Gaussians, and then use it to cluster out this data, and then put it in isotropic position. Because it's only in isotropic position as you have a good relationship between geometric distances and statistical distances.
So if there is a multiplicative epsilon gap, does it mean that statistical distance is also large? I just don't know what the...
Well, I haven't thought too much about the multiplicatives. I can tell you that in the additive case, if you have a mixture of 2 Gaussians, if it's in isotropic position, then the two are polynomially related. Their statistical separation and their geometric one. Multiplicative I'll have to think about, so let me get back to you on that. Yep.
When you say the computational complexity doesn't depend on the parameters of the Gaussian, or it depends?
Is a fixed polynomial in n and 1 over epsilon. Epsilon is your target accuracy.
Because if you have exactly the situation when they are geometrically, they are very close and very big variances in one direction, very small variances in the other
Right, so
direction.
the runtime, the algorithm only depends on the statistical separation properties of the mixtures of Gaussians. So your epsilon there would be the minimum statistical distance.
Yes, but you have to find the direction where they are separated, and basically if they are geometrically very close, you will have...
So, okay, so this is in the real RAM model. Even when you have them geometrically separated, these are the standard results of Rudelson and Bershainen, that you take n log n samples, and you can compute an affine transformation that puts the mixture in isotropic position. These are their standard, bounds on how close you get to the true covariance matrix. So once you have that, then you no longer have to worry about. So I agree. So the real RAM model, you have to be very careful with it, because each sample you're getting, it's modeled as actually a sample from the distribution. But the algorithm only has to look at a polynomial number of bits to actually be able to compute a linear transformation that puts it close to isotropic position, and then afterwards your worry is alleviated, right?
Also, I would like to ask, so what you are doing, you look at one-dimensional projections where we can identify something like multi-modal structure.
Yep.
And so...
Are you going to ask me about connections to projection pursuit, or?
No, almost. So what I mean is, so if you look at one-dimensional subspace with non-Gaussian behaviors, there is a negentropy, which is a characterization of non-Gaussianity, and you can use this fast IC algorithm to find such direction, and it's extremely fast and efficient. So you don't need to randomly select that.
So it depends on what your measure is. So for example, in ICA literature, when you end up using cumulants, these are, the precursors to a lot of the fast ICA types of things, then actually you can find directions which maximize the difference, of the cumulant compared to what it would be for the Gaussian. Now, if you use things like mutual entropy or, any of the other measures, then it's not known how to actually provably find the direction that maximize the difference. Now, there are techniques which seem to, but
Anyway, so the other question is, so you do one-dimensional projection, so you can think about two-dimensional, three-dimensional projections, which could be both non-Gaussian, and there is also a efficient algorithm which we call non-Gaussian component analysis, which actually is very much tailored to the same idea, to find the direction in which your distribution is different from Gaussian. So this is what I'm looking for, and so all you need is to find a subspace in which you can distinguish two or three mixtures of how many.
So I agree, but for example, many of the contrast functions within ICA, there are iterative approaches for trying to maximize them, but they don't necessarily maximize them.
No, so I mean, ICA is only one proposal. There are some other, and it could be a nice idea.
Could be, yeah, could be.
Any other question? So if not, I think we did a good job. Let's thank all of us.